any question I were to ask would be super easy. Awkward. It'll all be good. Did you guys have a class this morning? What do you have this morning?
At the study.
Okay. Now, Ronnie, I hope your background's set to blurry, because if it isn't, everything looks fine. Just saying. Yeah, look at all these blurry backgrounds. You wouldn't want me to see how clean your room is. Cough, cough. Yeah, Gene this morning, literally still clutching a pillow, but he was vertical, so it's a technical. All right, we're missing a couple here. Who are we missing? Dr. Pat, we're expecting. Geo. Okie doke. What else are we expecting? Okay, just a few. Who just joined? Jumps around. Dr. Malik, is that you? Wiggle your ears or something, so I know. Okay, we're just about there. But we've lost Josh and Deep. Well, fine. Just the way it is. Okay. Any questions at all that I can ask about titrations, you guys will know without using your phone. Yeah, I threw the phone part in there. Okay. Let's join. Just going to check here to see what's going on with this incredibly strange. Everybody has to boot up separately. Rem, is that you? Maybe, maybe not. The classic log in and go back to bed trick works not really well. Okay. Just gonna check there again. For some reason, some of you guys aren't logging in directly. It's sort of routing you somewhere, and I have to go around and find out where you are and bring you into the meeting. Okay. Just really waiting for one.
Charge complete.
You guys are pretty chatty today, right? Pretty talkative? Sort of fun people to associate with? Life of the party? Now, Anissa, I've heard you speak before. I guarantee it. I'm pretty reasonably sure that you can all... Yeah. You guys all have driver's licenses? I think you need them for some of those city jobs as well. Okay. So just give me a second here. Where is Dr. Pack? Okey-doke. Just gonna have a little nutrition here. Ah, dreadful. Okay. So I'm going to assume everyone has done physical titrations in the lab, right? Maybe in your basic? Okay.
Actually, I haven't. I missed that lab.
I see. Partying a little too hard the night before? Third day of a rave? Nice. Okay. Here's the deal. Titration is fancy pouring. Pouring one thing into another. In fact, using the exact volumes of what we pour to figure out a point where there's a conversion or a change. Dr. Pack, you're 9 seconds late. Oh, you're never going to make the JTF2 squad for that. All right, fine. And I don't think Rim ever logged in. I think I got a thing here, but there's no person there. Okay. So what we're going to look at today is titration. And although most of you, Dr. Paget, have done titration where you simply titrated in something, you had an indicator in them, and you looked for a point where the color changed. Is that about it? Something like that? And you had to figure out the volume and go to the front and see if it was right? Is this sounding approximately correct? You don't even remember that far back, do you? Anissa, I can see the look. Okay, fine. So I want to do a more comprehensive look at this for a number of pretty good reasons. Okay, let me just adjust your screen, get you over here. Everybody repaginates yet again. Interesting, but confusing. Okay, and I'll just fire you up there. Okay. Okay. Titration is a way of measuring. The primary thing you're measuring is volume. You're using a burette. They come in various degrees of accuracy and various degrees of expense. And today, I want to profile a buffer. But the secret sauce in today's discussion is you're not just doing a titration, very accurately pouring something into something else. In fact, the way we are going to do it is we're profiling all of the chemistry that goes on. And the extra secret sauce is that instead of having to do a bunch of calculations by hand, the way we're doing it is the graph that you generate will do the calculations for you, as well as illustrate the principles that I'm going after. So in the very, very crudest sense, a buffer or a buffer system is something that's going to resist change in pH. Not completely, not entirely, but it's going to resist changing pH. For example, if you were to take a cup of acid and pour it into clean water, the water has no chance whatsoever to defend itself. It has zero buffering capacity, which is why even a small amount of acid rain devastates a lake. There really is no internal or intrinsic buffering capacity. Okay. Note to myself, forget. Buffers come in a variety of source types. Some of the buffers you're going to use are buffers for molecules, so you're going to do analysis. For example, on HPLC. Some of your analyses may be on biomolecules or even living things. Those buffers will not only have to have an accurate pH, but have to have osmotic balance, the correct level of salts and sugars, etc. So buffers can go from an incredibly simple acid-based mixture to a very, very complex tris glycine, something we would use for a polyacrylamide gel electrophoresis. Fortunately for us, all these are well-established recipes, and many of them, you just buy the bottle pre-made and mix it up. Super easy to use. They'll help your cells survive. You guys, have you started Micro Lab last week? I know you have. You don't even have to bother, most of the questions I ask, I already have the answers. I'm like sort of, a federal prosecutor. I already know the answer to that. I've already talked to the folks. You cannot leave cells in straight water. You're probably using for dilutions peptone water or one of those buffers of physiological saline. Otherwise, cells will die. This also applies to biomolecules and to a lesser extent, just regular organic chemicals. We don't do a lot of reactions in pure water. So let's take a look here. The math, the part people hate, is the Henderson-Hasselbalch equation. It is the technical formal definition of pH. The reason I'm bothering you with this, because I'm not a big fan of annoying students with math. I don't mind annoying students. I don't like bothering them with too much math that's not focused. But this has come up in a question in interviews. I know Emergent has asked it. A number of labs have asked it. They'll say to you, could you please define pH? And, like, in a normal world, you'd say, well, pH is a measurement of the relative presence or absence of protons, which is true. But they're probably looking for something like, the negative log of the, they want a formal definition. So if you're asked that in an interview, be prepared to say the formal definition. Technically, pH is the pKa value, something we calculate, and I'll go into that in a minute, plus the log of the concentration of base over the concentration of acid. All of it revolves around the most fundamental principle in chemistry. Basically, all reactions are a variant of an equilibrium or balance, right? Things tend to go from high concentration to low. So take a look right here. This is the same kind of thing we see in most organic reactions, but in this ridiculously simple example, we've got an acid, which is made of an anion, something negative, plus a proton, and it is in equilibrium back and forth to the anion by itself free and the proton. And this balance is what actually goes on. And this will change depending on the pH of the solution. So if you're titrating and changing pH, and that's probably the single most common thing you'll ever do, titrating, you're really examining this relationship. The anion and proton together making an acid, and then the free proton and the anion by itself. Depending on the pH, different ones of these species will predominate. The balance is, and it's the exact same balance we do when we're looking at normal reactions. It is the concentration of products, protons times the anion, divided by reactants divided by the products. So there's two of them. And the secret is the Ka is really the dissociation constant. The secret sauce there? It's the balance point. And why do you care about pKa? Real easy. pKa is a value you look up, and it's going to be an indicator of acid strength. And that's acid strength in a functional way. It's really indicating the point. Well, I'll explain it in more detail, the equivalence point a little further in. So pKa is effectively the middle of this equation. Things are 50-50 on either side of it. But I'm going to show you graphically what that means in a minute. When you did your titrations so far, you basically were looking for a single endpoint. You were titrating in a volume of a known titrant into something. Did you have it? Did you mix by hand, or did you have it on a stir plate with a magnet? Stir plate? Magnet? Did you wash the magnet? I like to coat the magnets in acid or base to see if it wrecks your experiment because you didn't wash your stuff. Yep, I'll do that. Want to keep you honest. So here's the real thing. Have any of you ever heard of IEP? IEP, what is that? You'll remember next year when you repeat the course, or the year after that when you repeat the course. I'll try again.
Isoelectric point.
Are you sure? Fine, you win that round. Okay, fine. The reality is pH behaves in a very, very similar way. Take a look here. At the pKa, there's a pH where the acid and the anion mixture is 50-50. It is a perfect balance. Dominant charge is 0. If you add a lot of protons, you're increasing the positive charge. Hello, protons are positive. And so everything at a pH below the pKa, just like below the isoelectric point, will be positively charged, will be acidic. Okay? If you're adding alkali and removing protons, eventually you'll just have that unguarded anion. Or as fellow organic chemists, I bet you're thinking nucleophile. Fine, nucleophile, anion, same idea. And it becomes more and more negative. So if we're titrating and we go above a pKa value, the dominant charge in there becomes negative. If we're adding acid, or it's acidic to begin with, an excess of protons means excess of positive charge. We're going to have a dominant positive charge. So folks, just like the isoelectric point, there's only 3 conditions. A pH where it's neutral, charge is 0. My GPA as a graduate student. Below that, acidic, positive charge, excess protons, and above the pKa, or the isoelectric point, it is a negative charge. Are you good with that? Are we good with that? Yes, no? How long is this going to take? Well, you're probably going to go to 4:30 today, just to keep Geo honest. I'm trying to keep Geo off the computer more often, but it's a lot of work. Right, Geo?
David?
That doesn't sound like Geo. Geo, something wrong with you? Yes.
Okay, I'm having trouble understanding the difference between the pKa and the pH values.
Well, pH is a measurement, and the pKa is a pH point at which the charge is equal 0. pH exists on a sliding scale, right? Any value you want. The pKa is for that particular entity, those charges are going to be 0. It is the equivalence point. In fact, look, right here, 50% dissociation, so it's half and half. Kind of like an ice cream cone. It's half chocolate and half vanilla. I haven't had lunch, by the way. I'm pretty hungry, just saying. All right. If you were to look at this, and I'm zooming in here, I'm going to give you the real one in a bit, but if you were looking at this, conceptually, it's a lot different than titrating just to a single endpoint. The single endpoint says, here's your volume. You can figure out the concentration of something in that beaker. When you're doing a full titration curve, you're allowing the graph you're going to make to fill in every single point. So basically, you are getting a complete profile of the chemistry as it occurs. And the reason it's useful to use a graph is it will extrapolate and fill in every single point on that line. You're not measuring an infinite number of points, but the graph itself, using Excel or a spreadsheet of your choice, it's going to fill those in. So if you take a look here, let's start down here. Down here, it's pretty acidic. You haven't added much base. We're adding hydroxyl. It's pretty acidic. What's the dominant charge going to be? What's that? It's going to be positive. As you begin to add more base, you start to remove free hydrogens. And you'll notice, and this is important, and I'm going to hammer on this in a couple of diagrams, it actually slows down. At first, the first changes when you add base are fairly quick, but then it slows down. It slows down, and you keep adding base. However, everything is finite. You end up adding enough base, you start to mop up and remove all the remaining protons. Once all the protons are gone, there's nothing keeping the pH down. So what you see is suddenly it almost goes straight up. And there's a period, though, in between this little sort of bluish box where it's actually, ready, resisting change in pH. A buffer, for the purposes of this definition, is this flat-ish or flatter area where it's resisting change in pH. It is not perfect. No buffer resists pH like a flat line. Why? Because the buffer itself is being consumed molecule by molecule. What's happening is every bit of NaOH you're adding down here is removing protons. And eventually, just based on concentration, you're going to run out of protons. Once those protons are used up by the base, up it goes. The dominant charge is negative. When you hadn't added much base, you had a proton, it's positive. But in the middle, you have a squished area where it's a lot flatter. It'll never be perfect, but it's flatter. That is the area where buffering is occurring. We call that, ready, in quotes, buffering range. Buffering range. Look at you writing that down. You're not writing that down? You're going to remember it perfectly? Because on the lab exam, I'm going to do things like, in the context of what I said in class, what does so-and-so mean? So when you look it up online, you'll get it wrong. Isn't that mean? I know. He's like that. I'm trapped in him. It's horrible. So again, a titration curve represents all of the events, not just a single endpoint. You are literally observing in real time all the events. So you start off with lots of free protons. As you add NaOH, you begin to mop them up. However, there's an area where you resist it just based on the presence of protons, but eventually, based on concentration, you're going to run out of protons. When that happens, the pH is going to shoot up and become negative. So here's the part where it's a big advantage to you. You could calculate the pKa in a very, very horrible, long way with lots of math. But since the morning group started crying, I thought I would teach you the easy way. The easy way, are you listening? You draw a box around the buffering range, literally. In the dead center of it is your equivalence point. If you go left towards the y-axis, the pH, this value here will be the exact pKa value or the pH for your pKa value. It works exceptionally accurately. I would expect if we're in the lab, you could do this within 2 decimal places. It's one of the cases where the chemistry and the math line up perfectly. And if I had to choose between you doing this in the lab and a book value, and you got a slightly different value, I would back you up because you just did it on that day for those particular chemicals. Questions or thought on that? Thoughts? You're so full of communications, you can't even talk? Is that what's going on?
Wait, I have a question. Okay, how do I know the middle point, the exact middle point? I mean,
You use your
how do I
eyes.
know the?
I literally draw a box on it. And you can do that. You use the draw function in Excel, and then I just go to the middle of it. Look, can you not see the blue box? You can measure from side to side. The part you're uncomfortable with, doctor, is there's an arbitrary decision point where you say, this is flat and this isn't. You have to decide that. Right? Is this still flat or is this flat? You have to decide. It's just how the method works. Ironically, it still works incredibly accurately. It's just one of those things. It's if you're actually measuring the pH accurately, it is literally hard to get this wrong. Have any of you ever shot past the endpoint in your titration? No one here has ever done it. I find that hard to believe. Dr. Pack, you've never shot past an endpoint in your titrations? That you want to admit. It's extremely common. Well, I'll come back to that in a minute. So, just to be crystal clear, down here, the acidic, that's the anion and the proton, are dominant. The charge overall is positive. At the pKa, you've got the 50-50 dissociation. The charge is as neutral as you're going to be able to get it for that solution at this point in time. As you continue adding NaOH, in this example, you begin to remove the final protons. When those protons are finally mopped up, the dominant charge is negative. It's never going to be a flat buffering range. That does not exist. And in this example, this is literally the simplest example that I can use. Many of the buffers we will use in terms of handling, cell biology and handling clinical samples are a lot different than this. They have many different components. All right.
David, so you don't expect the pH to be 0 at the isoelectric point? It's going to be different for every compound?
No, the charge is 0 overall. The composite sum of the positive and negative parts cancel each other out for a charge of 0. That occurs at a specific pH. A pH of 0 is insanely acidic, and I'm not sure if you can technically get that many protons per unit. The pKa is a pH value at which the charges are 0, or it's half negative and half positive. Same thing, they cancel out. Gash and Deep, is that making sense? I just don't want to interrupt your phone, but just say it.
So at the pKa, there's a specific pKa value for every compound.
Yes, and for mixtures. And the thing is, even if you don't know for sure, you can titrate it, and it'll tell you the pH at which the charge is 0, no matter what. At the end of the day, as long as it's not filled with deadly explosive things, you can not know the chemical and still figure out its pKa value, where the charge will be 0, which has uses for analysis, for chromatography, for liquid chromatography, HPLC, etc. It has uses for advancing reactions or inhibiting them. It has lots of uses in organic chemistry. It's basically giving you a method to measure where that charge is 0, even for an unknown solution. Alrighty. So in the example, I would have you make up, 4 different solutions. And the 4 solutions are made of sodium acetate, acetic acid, and distilled water. And take a look here. Your first tube, number 1, has got sodium acetate, none, water, none. It's almost pure acetic acid. The next sample has 10 mLs of sodium acetate, 8 mLs of acetic acid. Then we have 16 mLs of acetate, 2 mLs of acetic acid. And the final tube is 0 mLs of acetate, 0 mLs of acetic acid, and 18 mLs of water. How good a buffer is water? I'll help you. It's El Stinko.
7.
All right. To do this for me, you would calibrate or standardize a pH meter. Why would you standardize the pH meter?
Verify.
Yeah, you're verifying, you are doing a performance evaluation and writing it down so you can demonstrate that analysis occurred within the performance limits, within the control limits for that experiment. I believe I talked about that last week. Lulu, did I talk about that last week? I did. But, you hear so much stuff. Who's going to remember? It's a classic example of you verifying analytical performance, and it should be on your resume along with lab balances, where you're demonstrating they work to a certain accuracy, spectrophotometers, and I think you guys said you have not used the Holonium filters yet for the specs. You might want to write this down. Holonium filter, HOLONIUM, Holonium. It's like polonium, but it's not delicious. I don't even eat meat. Come on. The Holonium filter, it looks like it is exactly the same size as a cuvette, but it has a very small grating in it. And when you put that into a spec and you hit scan, it literally scans every wavelength against the invisible markings inside there, and it'll do a profile. If anything's not functioning up to snuff, it'll let you know. So it's a very standard thing you do before using a spec. At the start of a day, you put this in, hit scan, and after that, you're good to go. It's not a substitute for a blank. It's simply suggesting that the way that spec works with respect to the amount of energy fired out and the receptors, the detector, it's working accurately. So a Holonium filter is a way of establishing machine performance. The blank is separate. The blank is to establish an analyte dissolved in a solvent. It's a different purpose. So, question for you. I've got some examples here. This in your book, I'd expect it to say table number 1, pH meter standardization, and then you've got known values in the buffer and measured ones. I have a question for you guys. How do you know when this doesn't work? What was the values you were shooting for? Awkward. Did you guys just do this like robots? Because you were told to? The worst reason in the universe? I can see worst reason in the universe is winning. How do you know when this number in the measured pH is wrong?
When it's way off with the expected value?
Sure. What's way off? 0.01? A million?
0.01.
I'm just saying, I don't believe you were given values, that you would have said that's my control limit, and beyond that, it's a non-conformance. So when someone has you standardize something, typically they will say plus or minus, for example, 0.2. Almost always you have to have a value. Otherwise, you've made a table, but you have no course to take if the numbers are wrong. How wrong is wrong? Is 4.3 wrong? Just saying. That never came up in your discussions? I'm going to go talk to Naga right now. I'll be right back. No, just kidding. I'm at home. I can't talk to Naga. I'll have to message him. Yeah, normally we have a value, though, just so you know, right? Because if it's wrong, we do a non-conformance report, and then we do a corrective action to fix it. Things you have to look for. You'll get people who will take the blue pH buffer and pour it back into the yellow bottle. And when you calibrate, you're telling the machine that that's a value of 7, and it's not. So the calibration activities are really important, particularly in a setting where you're actually sharing the same standards and passing them around. If one person puts it back wrong, you're all kind of out of luck. And there has to be a mechanism for you to catch that. Other questions? Do you guys like stirring with your pH meter probe? You're all looking really guilty. No one's ever done that, right? Where you've just, spin. No, never come up. That's the reason why we have exorbitant lab fees. Those things are $300 a piece. Please don't do that. All right. The way this activity works is you've got your solution in a beaker. It's got a clean stir bar in a cleaned beaker. It's mixing, and you're going to be adding small amounts of the NaOH solution. And the trick there is you don't even really need to be perfectly accurate because you can read the volume off of the burette. So I'd go a little shot, I'd read the number on the burette, and I wait a minute, and I read the number on the pH meter. And I keep doing that, a little shot from the burette into the mix, let it mix for a minute, and then I read the pH on the pH meter. What you're doing is you're adding measurable, defined amounts of the titrant into a mixing container, and after each, you're going to wait a few seconds, maybe 20 seconds, and you're going to read the pH when the meter's stabilized. What that's doing is giving you every single point on that line for the titration. Not 1 point, not 2 point, it's the whole thing. It's fundamentally different than doing a single endpoint titration where you just want the one number. What did you guys titrate for? Were you just looking for the one number for a concentration? Were you trying to quantify chemicals? I mean, you did this less than 6 months ago, right? Nina, it seems like 6 years ago? Okay, you might want to go back and write down your skills from your labs, folks. Just saying. So you're going to have two columns, the pH that you measure and how much NaOH did you add. You're going to highlight this, cut and paste it, fire it into Excel, and you're going to have a graph. Ronnie, this is what it would have looked like, but it would have been larger and probably messier in there, just knowing how you guys work in the lab. There's our clamped burette. One of the things I do is I expect everything in the lab to be labeled. If you don't label it, I will walk over with a red pen, grab whatever you're working with and yell, "We've got a winner!" Oh, yes, I will. I won't take marks away, but you need to know that an auditor, that would count every time. So if you've got a burette unlabeled, I'll spot it. If this beaker is unlabeled, I will spot it. And eventually, you'll get used to the sort of the sound of me saying we've got a winner. Now, one thing that's wrong in this diagram, we never, ever, ever just stick a probe in a beaker. The probe will be held by a clamp, either to the stand or to an articulated arm off the pH meter. Dropping this in so the magnet can go smash, 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 $300. Smash, 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 $300. Yeah, don't do that. We don't like that. Wouldn't you rather have like low or no lab fees? I mean, I think low is a pretty good target. All right, and what's happening? You're going to open the burette. You're going to have a few drops go in. You're going to read the numbers. That's it. That's all. So here's the important thing. This is the graph, the kind of thing that you would actually be generating. All right. You've got base. You're adding, you got acid. You're adding your base to it. You're measuring pH. It starts slow, and then you've got flat region. It's never completely flat. It's flattish, and it starts to go up. And you have to decide where are you going to put that box. I mean, literally, I've seen people very successfully just look at it, eyeball it, and say, this is the middle right here. Can you guys see where the middle is? Yes, no? Dr. Malik, you see the middle there? Go to the left, doot, 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 doot. And that pH is typically incredibly close to the theoretical value for the pKa. And that is telling you the pH value for that solution in the future. If you want zero charge, you're going to have to pH it to that value. If it's above it, it's going to be a negative solution. If it's below that value, it's going to be a positive solution. None of this is a surprise. It's something you control, it's something you measure, and something you can demonstrate. Period, right? Wow, so mean. What you're doing then is you're going to be making this into a graph. And the way it works is one of the little tricks I do in the lab is I say, yep, measure it till you're complete. How do you know when this is complete? There's no number in a single endpoint that you can walk over and say, is this correct? How do you guys know when it's complete? I'll just sip coffee for the 20 minutes it takes you guys to answer.
pH will increase abruptly.
It does increase, but then what happens?
Color change in the solution?
Well, here, let's even logically, when you've got a certain amount of protons in there, you start adding base. You begin to remove protons. You get the sweet spot where you're slowly removing protons because there's still a lot of them in there. Then you start to run out of protons. And every time you're removing them now, you're going up quicker and quicker and quicker. Finally, it's over. The end point in this, in making a curve, is I usually ask for 3 to 5 measurements once it's flattened out. Once the protons are all gone, it'll just be the pH of whatever you're titrating with. It'll be over at that point. So once you've got a flat line, you can keep adding base all day. But whatever the pH of that solution is where this is going to stop. So once you've got 3 to 5 measurements here, you've got the complete curve. The pKa is going to be in the middle of the flat region, over to the left. It's not hard. You require a standardized meter with values that you know are within your control limits for that test. And you need to write down these things in real time. It's not hard. The trick is, in most places, you're not running one at a time. For example, I'll have you guys running 3 of these at a time. So it's a busier piece of science than it looks like at first. Alrighty. I would have you on this graph, write down where is it neutral, where is it positive, where is it negative. Where is this going to be negative on this graph?
Right side.
Sure, of course.
From middle.
And where is it positive?
Left side from the first.
Yeah, and the neutral is your pKa. It's not hard. It's not confusing. It is a visual representation of how this occurs. And it's not unlike the way organic chemical reactions occur. You're looking for collisions, and eventually the reaction rate changes and slows down because there's fewer and fewer molecules available to react. So you can expect a whole bunch of action at first when the concentration is high, but to go to completion, those things have to collide, but at a much lower concentration. So typically, the last part of that reaction is going to be slower. Molecular availability dictates a lot of these things. So I got a couple questions for you guys. What buffer system offers the greatest buffering capacity and why? It'll be easier next year. Like, Ronnie, when we redo the course, you'll love organic by then. If you end up taking organic 3 times, I make you an EA. It's much worse than you think. It's truly horrible. A participation course says what? Seriously? What is a buffer supposed to do?
Treat the lion.
What is the one job of a buffer?
Resist the change in pH.
Sure. So what will be the greatest buffer?
Equal to the pKa.
Something can react with acid and base together.
Yeah, that's a true buffer. But what I'm looking for here is it resists the change the longest. If we were to take that same NaOH and put it in water. And I make you do this in the lab because you learn a good lesson. You're supposed to make a graph and figure out the pKa. Here's what happens, right? You put in 1 drop of NaOH into the water. The pH goes like this. Endpoint. Water has a buffering range of nothing. There is no buffering range. And in fact, it's at that one end of the scale. Some things have worse or better. The longer that slope, the flat area, the greater the buffering capacity, the larger the buffering capacity. It is ability to resist change. A true buffer, the ones I use biologically for cell biology, will resist changes of acid and base. They're a lot more complex than just a simple system we're looking at here. But the greater that flat, stable area is, the greater the capacity to resist change in pH. Again, in cell biology, we'll also, want to resist change and avoid osmotic shock, too much salt or too little salt. Oh, fellow microbiologists. So, no flat area, not even a buffer at all. Water is incredibly weak at resisting changes in pH. It's not a good experience. Identify 6 alternative buffer systems common to research. In the interview, if you're working at an emergent or one of the pharma companies, you're probably going to want to know 2 or 3 of these things in your pocket just for the interview, because those are the places where they do this and it counts. They're likely to ask you for the definition of pH and probably ask you for some examples. So bearing in mind, you want to be able to answer those things in a practical way. What kind of buffer conditions do living cells require? I know what you're thinking because you're in Winnipeg. Is it not freezing? Yes, not freezing is true, but I was thinking beyond the temperature.
Neutral?
Neutral in what sense? Non-MAGA? Or how do you mean neutral?
The pH is neutral, or?
Yeah, it's going to depend on the cell system. Also, again, the salinity has to be neutral. Physiological saline. Did you guys do any dilutions in microbiology yet? You would use bottles of Peptone water or physiological saline. The idea is the cells require that salinity or they will basically burst. Living cells will explode in hypotonic solutions of pure distilled water. You never, ever, ever use water unless you're trying to kill them. And I think Dr. Kong answered this. Why is pH meter calibration a critical activity? Because. Wow, you must have had a super exhausting communications class. Did you guys play on your phones so much you're speechless?
To verify.
Yeah, it is providing evidence that you are within defined limits. And again, in engineering and in science, we do this all the time. Your examples that should already be in your resume, certainly the pH meters, the balances with those little tiny weights, spectrophotometers with a halonium filter, and you will do more and more of these as you work your way through the various instruments. But you need to have practical examples. Because if you say, yeah, I did that, they're going to go, oh yeah, what'd you do it on? Saying in an interview is not the right answer. I even know the guy who taught you that careers course. Man, would he be mad right now. Yeah, Ronnie, I'm trapped in him. It's just truly awful. All right. Is water a good buffer? Easy answer.
No.
No.
No. It'll get things wet. It's fun to swim or surf on, but no, it's terrible. No capacity to resist anything. This is a thinking person's question. These are the kind of questions I like asking people. What are the strengths and weaknesses of titration assays? I know. You know what you're thinking? Blick, you jerk. You're expecting us to think? Yeah, you're good enough to have me hassle you in an intellectual way. You're worth me giving misery to, at least a little misery. So what's positive about this and what's negative? I know, I'll do one. Okay, negative side. It's boring. Haha. Back to you. I'm here till 4 o'clock. I could like even go get sandwiches and stay here.
Takes time.
Yeah, but not a lot. I mean, what test do we do that doesn't take some amount of time? Wow, I have to say, you guys are bad at this. Is it expensive? Where people do this wrong is they use a concentration or strength of titrant that is inappropriate for the thing they're examining. And I've seen this from many, many thousands of assays, particularly in the single point titrations where they shoot past the endpoint. It's classic evidence that the concentrations aren't correct for that assay. What about if the solution you're going into has an inherent buffering capacity itself? The assumption is that what we're working with is a pure chemical. Based on experience, it isn't often someone walks into the lab and says, "Can you analyze this pure water?" If they knew that's what it was, they wouldn't be coming to you. It's much more common to be analyzing a complex mixture. The counterpoint to that you didn't raise was, but Dave, since we're measuring all the points on the line, won't it still give us a correct pKa for that mixture? And I would say, Anissa, you're right. Dang! So the test itself will compensate for that unknown. It won't tell you what it is, but it will tell you for that given mixture on any given day what the practical pKa, the equivalence pH value, actually is. Alrighty. Questions or thoughts, you guys? I'm not going to give you the rest. I'm just going to ask you them on a test. That should get you nervous. You guys love tests, right? No. You don't? They literally pay me to do this, to judge you guys. Again, I won't have a surprise test. I'll pass the part in the notes and I'll say, now we're going to set it up for next week or the week after. We're going to have a review. I'll give you examples of how I structure questions. It won't be multiple choice or multiple guess. It'll be straightforward. I'll send the stuff out. You'll have a fixed amount of time to complete it as a Word document and send it back as a Word file with your name in it. Don't put it on SharePoint. Don't put it on the cloud. It has to be a Word file sent, emailed back to me. I'm not going to use a Dropbox. Email it back specifically. And it has to be before the deadline. If it arrives after the deadline, guess what your grade is? What's the charge at the isoelectric point? It's 0. I mean, it's just, so harsh. All right. Questions or thoughts? Is this your last class of the day? I think Dr. Kong is hosting a big barbecue outside.
I hope.
No? What's that? COVID restrictions say no? Yeah. My research group is working on Omicron. We're looking at the epidemiology of it. I happen to have lots of insider friends in the medical field, so we're getting data now. It's probably between 5,000 and 7,000 cases a day. They're simply not testing. The way I'm getting data is through information from the wastewater treatment. We're looking at the profiles of viable and non-viable particles based on RNA analysis there. Removing the restrictions arbitrarily without following the science is a mistake. Just saying. My doctor friends are grievously alarmed. They're already running at capacity. If I were to tell you how exhausting this is, in a clinical setting, I couldn't possibly exaggerate it. But to simply say, okay, it's good. Nope. Follow the science. Be safe. My family and friends are all doing that. We're going to stop masking and doing all that stuff when the science is there. So there. Alrighty. Who won the Super Bowl? Anybody watch that stuff? Biggest sporting event on earth? Well, the Americans say that, but I'm a big World Cup fan, so it doesn't really work that well. All right, you guys. I'm going to stop sharing since you guys are so communicative. And if you do want to apply for jobs, you need to be doing it now. Right? You will get some specific jobs from Mike Judge, co-op coordinator, as they become available for the co-op program towards the end. But any job you do, you can have that employer fill out the co-op form if it's a science job and meet that criteria. You require that completed form to graduate from this program. My advice is to do it as early as possible. It's not going to stop you from working next year. It's usually a big step up to getting a position next year. All right, you guys, I will be talking to you on Wednesday. I'm making sure that that lecture, because you talked so poorly today, I'm going to deliver on Wednesday afternoon the most boring lecture of your life. Oh, I know you think it was boring before. Just wait. I'm going to outdo myself. All right, you guys, I'll talk to you on Wednesday. Cheers.
Thank you very much. Bye.